now what we're going to do is we're going to transition into some of the case studies using the triboromeometry accessory and generate some data, so show some data that we've generated. The first case study that we're going to go into is the ring on plate, and what we did is we looked at different lotions. And so the objective of this test was really to compare the coefficient of friction of 4 commercially available lotions, and how does that pertain to how it feels when a person is applying this lotion onto their skin. The system that we chose was a Peltier plate and the ring on plate geometry. So we chose a Peltier plate because it's easy to control near body temperature. And then the surfaces, so as we've mentioned, surfaces are very important. So it's important to say what kind of surfaces we're studying. In this case, we did skin substitute on skin substitute, so then it's mimicking like a hand together or when someone's applying lotion onto their skin, rather than looking at the interaction between stainless steel and stainless steel. The samples that we used were Vaseline hand lotion, Aveeno hand lotion, an Olay Total Effects face lotion, and then the Eucerin body lotion. Again, all of these are commercially available. And then the test procedure that we did is we just did a simple flow ramp from 0.1 to 100 radians per second. So again, now our surfaces are going to start moving slowly and then again start gaining speed as they slide past one another. The load force again is 3 newtons because we want to just kind of simply mimic how much force an average user would be applying when pushing their hand to their arm or their leg. One thing to note is that this is a destructive type of test because, again, we're pushing these surfaces in contact with one another. So it's really good to change out the substrates for each experiment. So we would be replacing the skin substitute after each experiment. What we did find is that, so in this case we used the ring on plate, it's good to trim the sample to improve the reproducibility. Now, it's easy to load a large glob of lotion on the geometry, but all of that extra lotion around the surface, very similar to traditional rheology testing, is going to add a little bit of extra drag, which can increase your coefficient of friction. When we're looking and when we're thinking about tribology, we need to get out of this big bulk rheology type of thinking and focus more on a thin film, because that's really what we're looking at. We're looking at these microscopic surface asperities, how they interact with one another, and then how do they interact with one another in the presence of these thin films of lotions. So what we found is that trimming these samples is actually helping the reproducibility. So all I did here is I put some lotion on the skin substitute on the bottom plate. The ring itself was applied, had some skin substitute applied to the surface, and then they were brought in contact with one another. Took a trimming tool and just kind of scraped off all of that excess lotion around the edge. You may want to go on the inside a little bit too, but again, getting rid of that excess sample helps reduce the amount of excess torque during the test. So here's just an example. It's the same exact test, same exact lotion, 2 different loadings of the same lotion, but we trimmed it. And so as you can see here, we have excellent repeatability between sample loadings when we use that trimming technique. So you can see the dark blue and the light blue circles, they overlay really well with one another throughout the entire test. So now if we look at the coefficient of friction as a function of sliding speed, so again, coefficient of friction on the y-axis, the sliding speed on the x-axis, and this is studying different types of lotions, right? So in green, we have the Eucerin body lotion. In purple, we have the Olay Total Effects face lotion. The Aveeno is in orange, and then the Vaseline is in the blue. And as you can see from the pictures themselves, you can see they're actually quite different types of lotion, so we would expect different coefficient of friction behavior. And so again, we started at a velocity of, I think, 0.1 all the way up to 100 radians per second, and you can see the shape of the curves are significantly different from one another. What we did here is we kind of pointed out the application window, or the speeds which mimic most likely what people are doing, or the speeds that people are using to apply these lotions onto their skin. And so that's ranging from about 10 to 100 millimeters per second or so. Again, it's just a guess. But you can see here, so the Eucerin body lotion shows that it has a higher coefficient of friction through that application window, whereas the Aveeno hand lotion had a lower coefficient of friction. And so it's basically a way to quantify the fact that these lotions do feel different than one another. And then we actually did perform a sensory panel in-house with these 4 lotions, and it was in fact determined that the Eucerin body lotion felt a little thicker and greasier compared to the Aveeno hand lotion or the Vaseline lotions, which some people said felt a little bit more watery. But they're different kinds of lotions, one's for body, one for hands, so depending on the area of the body, you might want different properties of your lotions. But it is a way to distinguish between these 4 different lotions, and it does relate to how people are perceiving it when they're applying it. Another experiment that we performed, another case study, is in the realm of structured lubricants. And so in this specific study, we had 2 lubricants that were submitted, and we wanted to compare the coefficient of friction of them at different sliding speeds and also try to measure the static coefficient of friction. So the static coefficient of friction would be how much force or what's the friction that we need to overcome before it starts moving. So it's kind of similar to a yield stress of a material. In this case, we used the Peltier plate and the ETC because we did room temperature and then we did elevated temperature testing as well. And we used the 4 balls geometry because, as we mentioned, this is really great for lubrication type testing. All the surfaces were 1/2-inch steel or stainless steel spheres because this was being used in an engine type of application, so we wanted to mimic the surfaces that we were studying. The samples are lubricant A and lubricant B. And again, we did the test procedures. So in one, we controlled the torque. And then in another test, we controlled the angular velocity. Again, different temperatures, 25 and 180 degrees C. And then in this case, we did a much higher load force to mimic the application of these greases in the engine. Again, the substrates were inspected and cleaned thoroughly for each experiment and then replaced. So in this case, we did the static coefficient testing, and so you can see we have the coefficient of friction on the left-hand side, and then the sliding speed along the x-axis. And so this test specifically was a torque-controlled test, so we apply a certain amount of torque and start ramping the torque until we start seeing that the materials start moving past one another. So again, it's very akin to a yield stress type of experiment where we don't see any movement in our geometries until the yield stress is reached, or until stress higher than the yield stress is reached. Same idea, except we don't see any type of sliding speed until the static coefficient of friction is reached. So as you can see here in blue, we have lubricant A in triangles, and then in green squares, we have lubricant B. And the point at which they start sliding at 500 microns per second, so this is actually quite low speed, but you could see that that lubricant A is lower than lubricant B, or the static coefficient of friction of lubricant A is lower than static coefficient of lubricant B. So one could say that the lubricant A would be more effective at room temperature than lubricant B because it will start allowing the gears and the engine to start moving sooner. Okay, so why do we want to know about lubrication? What do we use lubrication for? Lubrication is the process or technique that you can use to reduce friction between 2 surfaces and when they're in relative motion to one another. So what you'd want to do is place a lubricant between those surfaces or some type of material. So this could be either solid or liquid lubricant. And it really is to reduce that friction between these 2 surfaces. So you can imagine how a car would operate if you didn't have any type of oil or lubricant in there. It wouldn't run very smoothly at all. So we're really happy about the study of lubrication. But the analysis of lubrication, you can look at 2 different things. One is the lambda ratio, and so this is going to be the ratio of the fluid film thickness to the composite surface roughness. So when we talk about those length scales of the surface asperities, the lambda ratio is the ratio of the fluid film thickness, so how thick is the film of your lubricant between those 2 surfaces, and how does that compare to just the natural surface roughness or the length of the surface asperities. The other thing that's very common is to look at the Strybeck curve, and so that's really a coefficient of friction as a function of sliding speed. So when we look at a Strybeck curve for a lubricated system, again, coefficient of friction on the y-axis, sliding speed on the x-axis, you'll see here that some Strybeck curves tend to look a lot like this diagram here. And you can see there's 3 very distinct regimes. The boundary lubrication, the mixed lubrication, and then the hydrodynamic lubrication, which we'll go into in a little bit. But the benefit of the Strybeck curve is that it really captures the coefficient of friction's dependence on load force and angular velocity. So now one of these tests you can perform just by increasing the angular velocity at a constant load force. And so you could repeat these steps, or you could repeat this test at different load forces to see how does the load force change or shift your Strybeck curve. When we talk about the boundary lubrication regime, so you notice that's at the very beginning of this Strybeck curve, we're talking about direct solid-solid contact between our surface asperities. So you can see here we blew up the picture in the bottom right. So in blue you have one of your surfaces, in orange you have another surface. Yellow is going to represent the lubricant in between those surfaces. Now those black circles are there just to kind of highlight the fact that these surface asperities are in contact with one another. And the load at which we're applying, right, so these are being compressed with a certain load force. That load force is being carried by these contact points, so the solid-to-solid interaction. You could see that the system is able to move at very low speeds in the boundary lubrication regime, and typically this lambda ratio is less than 1.2. So that really means that you have a very, very thin film layer compared to the surface asperities of your two surfaces. Now, the bulk flow properties of the lubricant will play little to no role in the wear because, again, it's just in between the surface asperities, but all that load's being carried by the contact points. And so in this specific regime, you could see we have a very high coefficient of friction, so it's a regime of very high friction and wear. Now, if we start moving to higher sliding speeds, now we can start moving into the mixed lubrication regime. So in this case, you have a little bit of contact between some of the asperities, but not all of them. So sometimes the bulk lubricant and the thin film between these surface asperities is going to be supporting most of the load. So you end up seeing a decrease in the coefficient of friction because now the surface asperities aren't scraping past one another. They actually have a lubricant in between them. So now the system's able to move at low to medium speeds, and then your lambda ratio is typically between 1.2 to 3, and then the regime is of moderate to little wear. This is typically seen by a big drop in the coefficient of friction, and then you'll see an increase in the sliding speed. So as you can see here in the graph, now if we look at those same surface asperities, now they're separated out a little bit because that lubrication, that thin film, is in between the surfaces. The last area of the Strybeck curve would be the hydrodynamic lubrication. And so now this is when we're moving at really high speeds and we have no solid-solid contact. So 100% of that load force is going to be supported by our thin fluid lubricant film. So you could see here in the picture, none of our surface asperities are touching one another. That lubricant is in between the surfaces and supporting all of that load. You could see the velocity is much faster than it was in either of the other two regimes. But we see this increase in coefficient of friction, and now you might wonder, it's kind of strange seeing that, right? Because all of our surfaces aren't in contact with one another. What's going on? Why is my coefficient of friction increasing? And it's actually because of hydrodynamic pressure. So as these surfaces are moving faster and faster past one another, now we get a little bit of turbulent flow inside of the fluid film itself. And so now that fluid's going to push those surfaces apart as it supports that load. So now we have an increase in the coefficient of friction due to the drag and those hydrodynamic forces in the lubricant. The lambda ratio in this area is greater than 3. And the system's able to move at really high speeds. But this is a regime where you see very little wear. So it's good to see, at what sliding speed does my boundary lubrication, my mixed lubrication, and my hydrodynamic lubrication areas start, because that will tell us, okay, how maybe this formulation is good for one specific application, maybe this formulation is not good for an engine, things like that. So in this specific case, if we go back to our data, now we're looking at lubricant A and lubricant B, and you could see here in our diagram we have very clear boundary lubrication regimes, very clear mixed lubrication regimes, and then you can see the coefficient of friction starting to increase when you hit that hydrodynamic lubrication regime. So you can see here, so we have lubricant A is in the light gray and lubricant B is in the dark gray. And all of this testing was done at 180 degrees C. So now this is at elevated temperatures. And what you could see is that lubricant B just has a constant lower coefficient of friction overall compared to lubricant A. And that the hydrodynamic lubrication regime is shifted out a little bit. So in this case, you could say that the lubricant B would be better used for high temperature applications. So in this case, what we're going to do now is kind of switch gears a little bit and talk about mouthfeel. So this is a relatively newer area that's coming to fruition, but as far as using tribology is concerned. But with mouthfeel, you want to look at how a product's chemical and physical interaction is within the mouth. So this is pertaining from all the way starting from the initial perception when that food or drink is first entered into the mouth, mastication as it's being chewed and moving from a large material down into smaller length scales, down to swallowing, and then even the aftertaste of what remains, so those thin films that remain in the mouth afterwards. And a lot of times this mouthfeel, not only is taste a big factor, but mouthfeel is directly related to whether a consumer will accept a new product or not. Oftentimes these are qualified using sensory panels, but the question is there a way that we can use tribology to not necessarily get rid of sensory panels, but to maybe weed out some formulations that may fail in a sensory panel? So without having to go straight to the sensory panel, can we use tribology to kind of quantify mouthfeel or at least get some idea of what's going on? So when we talk about food, right, we're looking at things going from macroscopic properties all the way down to surface properties, because you have these length scales, these hierarchies of length scales and structures inside of a food product. And as a consumer, as this food is chewed and swallowed, those length scales and those hierarchy structural scales are going to start breaking down. So when we're looking at macroscopic properties, you could think of, like, let's think about chocolate, for instance. When you have a macroscopic property, that's going to be something like a big chocolate bar, right? So maybe that's on length scales greater than 100 micron. So how is the snap of the chocolate bar? What's the modulus of it? But then when we move to bulk properties, now we're looking at less than 100 microns. So that could be more related to rheology and the interaction of the fat content and the crystals and how those interact with one another on that length scale. But then when we talk about surface properties, now we're looking at, the less than a micron into the nanometer range. And so that's going to be more in the realm of tribology. And so that's really those thin films that remain in the mouth or as someone's consuming these products. So for this case, we went with chocolate because that's everybody's favorite food. And we have, in this specific case, we wanted to compare the coefficient of friction of chocolate with varying cocoa content. So in this case, we had the ball in 3 plates geometry, and we used a 1/2-inch stainless steel ball in the upper geometry and skin substitute. So we took skin substitute to cover up the 3 plates, so then it kind of mimicked more of what was going on in the mouth. We looked at white chocolate, semi-sweet, and 100% cocoa, and again, did this testing at body temperature with a load force about 3 newtons. And again, to note, substrates were replaced for each experiment. So what we did first is we wanted to do just typical rheology. So we used a cone and plate, 40 millimeters, 2-degree cone, and we did a straight viscosity curve of these melted chocolates. And you can see here, so we have white chocolate in blue, semi-sweet in red, and then 100% cocoa in the green. And you can see that all the curves look really great. But if we use the Casson model to model these different curves, you could see that the yield stresses were a little bit different, but at the infinite rate viscosity, right, which would maybe mimic more of somebody swallowing, their infinite rate viscosities were very similar, ranging from 3.1 to 3.9 Pascal seconds. And so in that case, the chocolates were not very different from one another, but everyone knows that white chocolate and 100% cocoa are going to feel a little bit different when you're chewing them and when you're those thin films. So even though we had similar viscosity profiles, despite the differences in cocoa content, can we use tribology to distinguish the behavior of the different materials? And so that's exactly what we did here. So you have the coefficient of friction in the y-axis and sliding speed on the x. And we have the white chocolate in blue, the 100% cocoa in green, and then the semi-sweet chocolate in red. And as you can see here, they have very different behaviors as far as tribology is concerned. So one could say that tribology could be used as a way to get an idea and relate this to sensory panel results and try to get an understanding of what these will feel like in a sensory panel or quantify the coefficient of friction and mouthfeel. Another experiment that we did for mouthfeel was with yogurt. So we wanted to compare the coefficient of friction of commercial yogurts that had varying substrates and fat sugar content. And so in this case, again, we used the ball and 3 plates geometry. We did 2 actually different types of spheres to demonstrate how changing the surfaces would change the coefficient of friction. So we have a 1/2-inch stainless steel ball on skin substitute, and then we also have a 1/2-inch Delrin, or it's a type of plastic ball, on skin substitute. The different yogurts we used were 2 versions of Yoplait and then 2 versions of Faye yogurt. And then in this case, we actually just did peak cold. So we wanted to just do 1 constant rotational rate and to see what the coefficient of friction was at that specific rate at a load force of about 1 Newton. So the way that these 4 yogurts differed, we wanted to make sure that we had some baselines. But the Yoplait yogurts actually have added sugar and cornstarch, which are used as modifiers. And then the Yoplait original contained gelatin. The amount of protein was differed in each one as well. And then we threw in a Faye Greek 2% yogurt to compare with the Faye non-fat yogurt to see what the effective fat content was on friction without changing any other variables. So as you can see here, we've got all of our different types of yogurts. Some included cornstarch, others didn't. They had different sugar contents, different protein contents, and different fat contents. But you could see with the Faye yogurts, the only difference between them was the percent fat. So what happened? Well, we have the coefficient of friction on the left-hand side, and then we have time on the x-axis. And first, what we have in triangles is the steel on steel. So this was a stainless steel sphere on a skin substitute stainless steel plates. And you could see here, so in dark purple, we have the Faye Greek non-fat versus the orange, which is the Faye Greek 2%. And so that had a little bit more fat added into it. The Yoplait Greek vanilla in green, and then the Yoplait original French vanilla in blue. And you could see that the French vanilla had the lower coefficient of friction, whereas the Faye Greek non-fat had the highest. But the Yoplait Greek vanilla and the Faye Greek 2% had actually very similar coefficient of frictions throughout the entire test. Now, if we change the surfaces, because we've been harping on the fact that changing surfaces will change the coefficient of friction, if we look at the different surfaces, now we have a Delrin ball on transport tape. So again, the Delrin ball is going to be a little softer than the stainless steel sphere, but you could see here that the trend is actually quite similar. So even in this specific case, the coefficient of friction quantitative value is different. The trend between all of them is still the same in this specific case. So we have the Faye Greek non-fat had the highest coefficient of friction, original French vanilla had the lowest, while the Yoplait Greek vanilla and the Faye Greek 2% had similar coefficient of frictions in the middle. But again, you could see here that the coefficient of friction is greatly impacted by the difference of the surfaces. So in summary, the coefficient of friction is not a material property, but it is a system property. So it will depend on the 2 surfaces that we've selected, the characteristics of the surfaces themselves, what kind of lubricant, whether there is a lubricant, what type of lubricant, viscosity of the lubricant, and then what are the testing parameters that we're looking at? What are the load forces, the temperatures that we're testing? So all of those are going to affect your coefficient of friction. But what we've proven is that this triboreometry accessory is able to quantify the coefficient of friction on our rotational rheometers in very many different applications. So we looked at tactility, lubrication, and mouthfeel. The coefficient of friction as a function of sliding speed will depend heavily on the interacting surfaces in the lubricant. It will depend on the temperature, but we also saw that by using a torque ramp, you can quantify the static coefficient of friction with our materials, which is great, and that it is kind of akin to a yield stress type of test. And then lastly, if we have consistent sample volume and loading techniques, we can enhance the repeatability of these measurements. So all of that excess sample around the geometry can add those drag forces, which will give a slightly higher apparent coefficient of friction. So if you have any questions about tribology, or you want to get in touch or find out more about what TA has to offer, visit our TA Tech Tips on YouTube. We have a lot of great short videos of how to set up certain tests and introductory to certain accessories as well. If you're interested in this specific accessory, you can contact your local TA sales representative or our applications at tainstruments.com. And then if you're interested in any type of on-site training or e-training courses, make sure to check all those out on our website, www.tainstruments.com. And thank you for your time.
Thank you, Alina. A recorded version of this presentation will be archived and available through the TA Instruments website.